All right, so I want us to imagine a situation here. Imagine we've got this function, and let's imagine that we wanted to know the value of f of x plus h. So let's actually start here. Imagine we want to know the value of f of x plus h. We want to know how high the function is high here, over x plus h, up that many units. But let's also imagine that the actual act of computing the function value at this point was difficult. Imagine it was just going to be like a cumbersome computation. It wasn't going to be easy. Imagine it's frankly not even computable. In cases that we're going to see, it's just going to be a difficult computation. But let's just imagine this is a difficult thing to compute. So you really don't want to just take x plus h and plug it back into your function. But now let's imagine this. Imagine that we had a point x that was nearby our x plus h. And imagine that point x. Imagine we could compute f of x very easily. Imagine it was very easy to get a grasp on how tall the function is tall at f of x. Imagine that was a known thing, not difficult to compute. In fact, imagine it was very easy. Imagine it was also easy to compute the derivative at our point x. Well, if it's easy to compute our derivative at our point x, then it is doable to find the tangent line. So here, in blue, is the tangent line at x. So at x, our tangent line to our function is this blue line. Now, also imagine, just for the sake of keeping things tame, let's imagine that our h was small. So our h is just the value of difference along the x-axis between the point that we know and the point that we're after computing. Well, here's the thing to think about. My claim is that whenever you process this all, that the tangent line and the function are very close in value. At x plus h. Because h is small, because our point at x plus h is close to our point at x, the tangent line is only going to be different from our function a little bit. Like, take a look at this. Let me zoom in on this, because hell, it's actually kind of difficult to see without zooming in. So let's imagine we've now zoomed in on that box. Our original function is coming through like this. Our point at x is right there. Our point at x plus h is here. And our tangent line is coming through like so. Our tangent line at x plus h has a value, and that value is really close to f of x plus h. But here's the thing to think about. If our f of x was easy to compute, if our slope was easy to compute, it's going to be easier to compute the point on the tangent line than it is the point on our actual function. Because the point on our actual function was difficult to compute. We're trying to avoid that at all possible. So the question then is, can we find the function value along that derivative? And I claim we totally can, because if we can zero in on this point here, like this value is close enough. It's real close to our value of interest. There's only a small margin of error. Let's try to find what that value is, because this value should only depend on a function value that's easy to compute and a derivative value that's easy to compute. So let's think about that. What is this value? To find this value, consider the following. Change in y over change in x equals slope, right? I mean, this is what you know slope to be. So if you multiply both sides by change in x, change in y is just m times change in x. This is, I mean, a fact, right? But what would this describe? This slope refers to between 2 points, A constant rate of change, which is what's occurring on our tangent line has a constant slope. So if we want to know how far we move vertically, as long as we're moving across our line, all we need to know is our slope and how much we're moving horizontally. So actually, when we're looking at this picture here, the difference between our f of x value and our value along our function, I tell you what, let me hash that in blue so you can see that it's coming from our dashed blue value. The difference there is just some change in y, but that change of y is given by the slope plus the change, or slope times the change in x. So this value here is just going to be our f of x plus some change in y. Well, that means our linear approximation estimate is going to be f of x plus change in y. That's going to be f of x plus change in y is equal to m times delta x. Well, let's think about this though. What is our m and what is our delta x? We know our f of x is just our function value at our point of interest. Our m is our derivative. Our delta x, how far we moved along the x-axis, that is our h. And our long story short is, if we want to use our line to estimate the value on our function that we couldn't compute easily, we could exploit our tangent line and our point that we know that is easy to compute, and we can say then, the value along our tangent line is just our original value at x plus some difference in y, and that difference in y is going to be, using our slope formula, just our slope times our change in x. Our slope is our derivative, our change in x is our h. And the long story short is we can always approximate along a tangent line using this formula, and heck, we'll find this very useful, as we'll see.